For the final lesson in this unit, we're just going to revisit Pythagorean theorem and figure out how it works with these right triangles and just discuss one way that it came about. So we see the right triangles below here, triangle with the ABC labels on it, right in here in the center. And if we write down the Pythagorean theorem for it, we would say that a squared plus b squared equals c squared. Okay, and then if you just draw squares that represent the areas for each one, basically what we're doing is taking side A and making another side A that turns it into a square that's adjoining the triangle on that side. We'll do the same thing with side B and the same thing with side C. So you've got three squares, one of each attached to the sides of the triangle. Now every product can be thought of as representing the area of a rectangle or a square, so we should be able to represent this by looking at the corresponding rectangles. So exercise 2. For each product shown below, draw and dimension a rectangle that has a product as its area. So if you've got 3 by 5, you can show that with a 3 and a 5. You could orient it however you want to. 10 and an x would look like this. X squared would look like this. And the final piece that we need is how we do similar triangles. So first off, if the altitude is drawn to the hypotenuse of a right triangle, it does split it into two lengths. So this one is splitting into a 3 and a 9, which means the total was 12. Find the length of the shorter leg of the right triangle. So the shorter leg is this AB segment. If we then reorient the small triangle to also contain AB but on the hypotenuse, we can say that hypotenuse is 12 over x equals short legs x over 3, and we can get the short leg 6. So that's something that we've done a couple of times now during this unit. All right, so we're ready to prove Pythagorean theorem using what we know about similarities. So if we take the diagram, the right triangle now has that altitude drawn in. The original hypotenuse was C. It was a triangle ABC. And we've split it, but we don't know how the split occurred, so what the numbers were on each one. So we'll say a D and an E as variable lengths. And if we redraw those triangles and orient them the same way, then the small triangle is going to have A as its hypotenuse, and it's going to have D as its short leg. The medium-sized triangle is going to have B as its hypotenuse and E as its long leg. So to set up a proportion, we can say that C over A, which is big hypotenuse over small hypotenuse, is equal to A over D, which is large triangle short leg over small triangle short leg. So that would give me a cross product of A squared equals C times D. We can do the same thing with a larger right triangle. We would say that hypotenuse B and hypotenuse C go together, and long leg B and long leg E go together. So B squared would equal C times E. And if we add those two equations, A squared equals C times D plus B squared equals C times E, we would have A squared plus B squared equals CD plus CE. All right, but that would factor. So that's C times D plus C times E. You can factor out a common term of C there. So there's the equation that we have at this point. And we already know that D plus E is the same as C, because if you look back here, we split it that way. The original segment C was split into D plus E. So if we replace that sum with another C, we'd have C squared on the right side, and that proves Pythagorean theorem. If we redraw it, we can show that that rectangle C times D here, and this rectangle C times E here, makes up that C squared, which is what we were looking for. So that's just one way to prove Pythagorean theorem. If you were to do a search online about Pythagorean theorem proofs, you would find hundreds of them. There are so many different ways that it's been proven over time, so it may be of interest to you to find another one and go through it and see why it works. But it's been shown many different times, many different ways that Pythagorean theorem is in fact valid.